that were developed for this unmanned spacecraft. These class of satellites were designed as a 1U CubeSat form factor. However, as soon as the initial design was complete, a limitation was discovered because there was not enough power in the geometry of the satellite to cover the demands of real-time video transmission from orbit. So we tried to solve this limitation using these deployable solar wings. However, this solution required the use of big batteries, bigger than any battery array ever built or available at that time for a 1U CubeSat, and even for bigger CubeSats. So calculations indicated that we will need a battery of at least 26.6 watts per bank, and as per system safety guidelines, that will turn into 4 of these banks, requiring a total of 106.5 watts. The challenge was to pack this much power into a space small enough to fit into a 1U structure. Sorry. This is tricky. Okay. Guidelines were capability of operation with batteries and solar power only. That's for the IPS system. Capability to manage 32 battery cells distributed into battery arrays for a total of 20.8 amps, or about 107 watts, with MCU-driven core and 8 solar input power channels, each capable of supporting 6 volts at 2 amps and 25 milliseconds switching capability. That's for EPS. The EPS card will manage all the power operations, so we'll need a big power tank without any control circuitry on it. So many challenges arose from these requirements. To locate lithium polymeter cells of the right geometry of length, width, and thickness to fit into a PC104 form factor with a maximum thickness of 7 mm rise per phase, or a maximum 20 mm thickness per card, and with the maximum possible energy density constrained by right geometry, and a containment method to avoid the natural swelling of the cells in vacuum. So we can see there's one cell in the vacuum chamber, and a fixing technique dependable enough to avoid separation of the cells from the PCB boards to swell. As it turned out, no cells in the commercial aerospace market could satisfy A and B conditions, so we could locate a manufacturer, and we achieved this length, 42 millimeters width per cell, with 19 millimeters thickness, 5 millimeters, and a capacity of 900 milliamps. Solved A and B conditions. Conditions C and D remain unsolved, so encapsulations of the cells in a hard metal case was out of the question due to weight, dimension, and manufacturing consideration. So it will complicate also solution D. So we solved the problem by shrouding each cell in a thin copper layer in order to be able to solder the cells to the copper substrate of the PCB. And at the same time, the tensile strength of the copper will help greatly to contain the swelling over the minor axis of the cells if we solder each cell to the PCB and then every cell to each other at the same time. However, this technique is simple and easy to manufacture, and that by itself solved the 2 remaining conditions still needed to be tested. The final prototype showed a roughness and a strength beyond our expectation, being able to withstand crash tests up to 300 G without us being able to destroy the prototype, and we did try hard. Our tests include freezing cells down to minus 32 centigrades for 48 hours, and then being heated by radiant light to 65 centigrades for 2 hours. Both tests were successful, and this is the copper shroud already soldered each other to this piece. Here is another view. Each battery array packed 8 cells per side for a total of 16 cells per pack. The resulting final nominal power delivered was 53.20 watts. Both satellites included 2 of these arrays for a total nominal power of more than 100 watts. One of the most important factors in a battery is the ability not to only being able to pack a very high energy density, but also to deliver it. That's why we use these pins to connect every cell. So, I mean, using cables could go, actually. And each battery array has 32 pins, so APS was able to control the charge on every cell. Due to the COM and COG design of our spacecraft, the battery arrays were mounted on the outer side, as you can see here, to mathematically maintain COM and COG. And also, they were very effective as a shielding, radiation shielding. Also, coupled with our linear shielding for the satellite. And we also used the mass of the batteries as a thermal sinks for the electronics waste heat, solving the problem of heating the battery during the week. To this end, we designed a carbon nanotube thermal transfer tube in order to route the waste heat from the electronics directly to the mass of the battery. And such bus will require us to cover the battery arrays in a thin layer of carbon nanotubes over a layer of graphite applied directly over the copper shrouds, as you can see here. To avoid the heat from escaping to space, the laminar distribution and the big radiating surface, we put some laminated mylar, gold acid mylar. And once completed, more thermal vacuum tests proved that the swelling containment technique was working pretty fine. Look at there is no deformation. This is in vacuum. The 55 Cs by 3.610A minus millibars for 24 hours. The final parameters is as you can see here. We can check this because I'm running out of time. The tests, many vacuum thermal tests confirmed the design to be sound, allow the array to operate with full payload electronics turning continuously. We can see the next chart. This is for 2 battery banks and 1 battery bank. This is like 50,000, yeah. 48 hours continuously. And this is the other. This is a simulation of the whole 24 orbits cycle. You can see here the temperature of the batteries in up and down and exchanging heat, right? This you can check all in the paper. So, okay. In orbit testing, the first satellite was launched, and then it worked properly. We can see here. Until we have an anomaly in orbit caused by an unknown object. There's a paper on this. The damage of one of the deployable solar arrays and the deformity of the main antenna. The spacecraft survived the event by remaining out of contact and without altitude control for about 6 months until we were able to recover the signal. But an altitude control loss also meant that the satellite could not charge the batteries as it could, not point the large solar arrays properly to the sun, so the batteries were actually depleted. Surprisingly for everyone, once the satellite could regain altitude control, the batteries started to charge again. Although the antenna damage remained, the spacecraft continued transmitting the beacon, as our APS included a feature that allowed the system to operate on solar power only in the event of the battery getting completely beyond the charge. So at the same time, the satellite operating on solar power provided electronics waste heat needed to prevent the batteries from freezing, thanks to the thermal transfer bus system, thus greatly contributing to the battery life and utility recovery. And this intended test of our battery arrays show that our engineering worked in ways that we did not foresee. and the design guidelines proved to be sound. In March 2016, we were selected to provide these batteries to the U.S. public schools based on program, comprising 12 one-year Cubesat launch among 14 years to provide, among other things, the panels and also the batteries. The main launch of RR.PP is to take place in March 2017, some signals are. And this is a new battery generation. They are scaled down for the design of RR.PP, the American satellite. This battery finished. It's pretty slim. This is the test we made on the batteries. It's also the battery banks. This is where the active banks that were delivered to the customer. And what we delivered was not long ago, passed the test with flying colors. And thank you for your attention. I'm open to questions.
Any questions from the audience?
I have one question.
Yes.
Could you tell me, how did you measure the swelling of batteries? Did you actually measure it?
Yeah, as you saw, the chamber was a small chamber, transparent. So we use lasers to see if the interference from one side to the other was first an interference with a grid, and then the other. Taking pictures of how was, of our spectrum, for both sides.
Excellent. Thank you. Is there any other questions on that?
I've got one more. Do you have any indication of the lifetime performance of this battery?
Well, actually, the batteries are still alive more than 3 years now in orbit. It's surprising for us. It's surprising, but they are still working.
And can you see any degradation in the performance?
Yes, we see degradation, but a very slow degradation. Actually, what I report is that the same cells of the same batch that were acquired 5 years ago are still in service here on Earth, and being used on drones. So 5 years now, those cells.
Okay, thanks very much. I have one more question actually. You mentioned an event that occurred after launch, which damaged your satellite. How long after launch did that occur?
We launched on April 25 and it occurred on May 22.
So you don't have any indication what caused the...
We did investigation on paper actually with the chief scientist of IAC, Thomas Kelso, that was from Telestra. We came to the conclusion that someone hit something, but maybe it was a micrometeorite, not exactly the event. Our close approach was pretty near, 5 meters. But 22 hours earlier, Goes 13 suffered this exact same anomaly, the same behavior. And at that point, the extraordinary meteor shower was winding down. So NASA had the same theories about, not the same theories about what happened to Goes 13. So it's probable that was the event that damaged the satellite.
Okay, well, remarkable recovery.
Thank you.
Thank you very much.
Thanks to you.
Oh, I think there's one more question over there.
Can I ask a question?
Yes.
Can you tell us a bit about the process in selecting your cell manufacturer?
Oh, well, actually, we first needed to know who can fabricate these cells on the right geometry we need. And actually, this manufacturer in Germany was the only one that could do it. So that was the selection process.
Okay, thank you.
Thank you.
Any more questions from the floor? let's congratulate.